For most of human history, the universe seemed eternal and still. The stars above were fixed in their constellations, the planets moved in perfect harmony, and the heavens were imagined as a grand, unchanging dome. Philosophers like Aristotle believed that the cosmos had always existed and would always remain as it was, perfect and unmoving. Even as telescopes revealed more stars, more worlds, and the vastness beyond imagination, the idea of a steady universe remained unchallenged. Space was seen as a stage, an empty arena in which matter performed its dance, but never something that could itself change. Then came the revolution that would quietly unravel this ancient certainty. In the early 20th century, a man named Albert Einstein introduced a theory so profound that it reshaped not only physics, but the very concept of reality. His equations of general relativity, completed in the year 1915, described gravity not as a mysterious force pulling objects through space, but as the very shape of space itself, bending in response to matter and energy. The fabric of the universe was no longer a rigid background. It was alive with geometry, stretching and curving as stars and galaxies moved within it. When Einstein first wrote those equations, he noticed something strange. The mathematics refused to describe a perfectly static universe. His equations demanded motion. Space itself had to either expand or contract. This idea seemed absurd at the time. The prevailing belief, supported by centuries of philosophy and astronomy, was that the cosmos must be eternal and unchanging. Unable to accept such a radical conclusion, Einstein modified his equations by adding what he called the cosmological constant, a term that balanced gravity perfectly so the universe could remain static. Later, he would call this addition his greatest blunder. While Einstein wrestled with his equations, another quiet revolution was taking place through the lens of a telescope. On the slopes of Mount Wilson in California, Edwin Hubble was studying distant galaxies in the 1920s. By examining the faint light from these galaxies, Hubble noticed a peculiar pattern. The wavelengths of light were stretched, shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther away a galaxy was, the more its light was redshifted. At first, redshift could have meant that galaxies were simply moving away through space. But when Hubble plotted the relationship between distance and redshift, he found something extraordinary. Every galaxy seemed to be receding from us, and the rate of recession was proportional to its distance. The farther a galaxy was, the faster it appeared to move away. This pattern could not be explained by random motion. It meant that the fabric of space itself was expanding. This realization shattered the illusion of a static universe. The cosmos was not a fixed arena filled with moving objects. It was the arena itself that was changing. Space was stretching, carrying galaxies apart like dots on the surface of an inflating balloon. Hubble's discovery in 1929 gave birth to modern cosmology. What had once been a philosophical question about the heavens became a measurable phenomenon, a physical reality that could be observed, calculated, and tested. But this discovery also posed a question so deep that it continues to challenge our intuition even today. If galaxies are moving apart because space itself is expanding, then what exactly is expanding? And more puzzling still, into what is it expanding? These questions touch the edge of human comprehension. We are used to thinking of things expanding into something else, a cloud spreading through air or ripples across a pond. Yet when the universe expands, there is no pond, no air, no outside. There is only space itself, growing in its own dimensions. The moment this truth was recognized, physics entered a new era. The universe was not a static collection of stars, but a dynamic, evolving entity. Every second, every breath, every flicker of light happens within a cosmos that stretches invisibly around us. The night sky is not silent or still. It is in motion on the grandest scale imaginable. The very distance between galaxies grows as time moves forward, governed by the same equations Einstein once tried to keep still. What began as a reluctant mathematical prediction became the foundation of modern cosmology. The expansion of the universe is now one of the most confirmed and measured facts in science. Yet, even with all our data and theory, one question lingers like a quiet echo across the cosmos. If everything is expanding, where is it going? To answer that, we must first understand what space truly is. Not as emptiness or background, but as a dynamic, physical structure that can stretch, curve, and evolve. The path to that understanding leads us deep into the geometry of reality itself, where distance, time, and gravity are not separate ideas, but woven threads of the same cosmic fabric. In the years that followed Hubble's revelation, the scientific world faced a profound reckoning. The universe was no longer the eternal, unchanging stage humanity had always believed it to be. It was alive, evolving, expanding. The discovery transformed our understanding of everything, from the smallest atom to the vastest galaxy cluster. It was as if the cosmos had suddenly taken a deep breath after billions of years of silence, and we were just beginning to hear it. Einstein, once skeptical, revisited his own equations. When shown Hubble's results, he is said to have sighed and admitted that removing the cosmological constant might have been wiser. The equations of general relativity, left unaltered, naturally predicted an expanding universe. Einstein's greatest blunder had been his lack of faith in his own mathematics. The irony was poetic. The man who had reshaped space and time themselves had momentarily resisted their dynamism. But science, unlike philosophy, corrects itself. The evidence was too powerful to ignore. As astronomers measured more galaxies, the pattern held true everywhere they looked. No matter which direction they turned their telescopes, the universe appeared to be expanding uniformly. There was no privileged center, no point from which everything flew outward. Every observer, anywhere in the cosmos, would see the same pattern: distant galaxies receding in all directions. This was the most humbling truth of all. The universe was not expanding from us or from any one location. It was expanding everywhere, equally, in every corner of space. To understand what that means, we must abandon a deeply ingrained intuition. We imagine expansion as motion through space, like a rocket leaving Earth or a balloon drifting through the sky. But cosmic expansion is not motion through pre-existing emptiness. It is the stretching of space itself. The galaxies are not flying away through a vast void. The distance between them increases because the very fabric of the cosmos grows. This distinction may seem subtle, yet it reshapes how we think about reality itself. Consider the image of dots drawn on a balloon. As the balloon inflates, the dots move farther apart, but none of them travel across the surface. They stay in place relative to the rubber, while the surface itself stretches. To a tiny being living on that two-dimensional surface, it would seem as though the entire world was expanding. There would be no center on the balloon's surface, and no edge to move toward. The expansion would be everywhere, uniform and endless from that perspective. In much the same way, our universe expands, not into an outside, but within itself. In those early decades, scientists were only beginning to piece together the implications of this discovery. The expanding universe suggested a startling idea. If space is stretching today, then in the past it must have been smaller, denser, and hotter. Run the clock backward far enough, and everything we see, every galaxy, every atom, even light itself, must have once been compressed into a state of unimaginable density and temperature. This realization gave rise to what would later be called the Big Bang theory. At first, the term Big Bang was meant as mockery. The British astronomer Fred Hoyle, who believed in a steady-state universe, used the phrase on a radio broadcast in 1949 to describe his rival's model. Yet the name endured, not as ridicule, but as a symbol of one of the most important insights in the history of science: that the universe had a beginning. It was not eternal or static. It had emerged, and with it, Time and space themselves had come into being. Hubble's discovery did more than alter astronomy. It changed humanity's place in the cosmos. We were no longer inhabitants of an eternal stage, but participants in a cosmic story with a beginning and an evolution. Every photon of light we see, every atom in our bodies, is part of that grand expansion, a ripple in the unfolding of space-time itself. From the faintest nebula to the largest cluster of galaxies, everything moves with the same cosmic rhythm. And yet, despite all the clarity that mathematics and observation provided, one mystery grew stronger, not weaker. If space expands, what is this space made of? If it stretches, does it have substance, or is it purely geometric? How can something that is not a material expand as though it were a fabric being pulled apart? These questions would lead scientists toward one of the most profound revolutions in thought, the realization that space and time are not containers, but dynamic elements of reality. The 20th century had witnessed the death of the static cosmos. The next step would be to understand what had replaced it. Not a void, not emptiness, but a living geometry shaped by energy, matter, and the passage of time itself. The new question was not simply how the universe expands, but what it means for space to have a structure that can grow. The answers would emerge slowly, through decades of theoretical work and increasingly precise measurements of the sky. Yet even in those first years after Hubble's discovery, one truth had become inescapable. The universe is not a place where things happen. The universe is what happens. Its expansion is not a motion through the void. It is the transformation of reality itself. The expanding universe became the foundation upon which modern cosmology was built. Yet even as this revelation spread through the scientific world, its meaning was often misunderstood. To say that space expands sounds deceptively simple, but beneath those words lies a profound transformation in how humanity conceives of existence. The shift was not just mathematical or observational, it was philosophical. It demanded that we let go of the last remnants of an ancient worldview, the idea of a cosmic stage distinct from the play unfolding upon it. When Einstein's equations are written in their pure form, they do not describe objects floating in a pre-existing emptiness. They describe the fabric of space-time itself, a four-dimensional continuum where distances and durations are not fixed but depend on the geometry of reality. Matter tells space how to curve, and curved space tells matter how to move. This relationship means that when galaxies drift apart, it is not because they are sailing through a void, but because the very measurement of distance between them changes. Space is not a static backdrop, it is a dynamic participant in the cosmic story. This realization introduced an entirely new kind of question. If space itself is dynamic, then what are its properties? Can it have tension or energy? Can it curve and evolve the way a surface can ripple or bend? General relativity answers yes to all of these. The curvature of space defines how gravity behaves, and the energy stored within that geometry determines how the universe changes with time. Space is, in a real and measurable sense, something. It has structure, it has influence, and it can expand. This is where the story becomes difficult to grasp through intuition alone. Our minds are used to imagining expansion as something that occurs within a larger setting. A gas expands into a room. A balloon expands into air. But cosmic expansion is different. It does not require an external space to move into. The universe expands as its own geometry stretches. There is no edge being pushed outward, no frontier being crossed. Instead, every region of space expands in relation to every other region. It is a change in the relationship between points, not a journey into the unknown. As observations improved through the mid-20th century, astronomers confirmed the details of this cosmic expansion. They measured the light from galaxies billions of light years away and found the same pattern Hubble had seen, a redshift proportional to distance. The farther the galaxy, the greater the stretching of light. Each photon that reached Earth had traveled across an expanding sea of space. its wavelength stretched by the growth of the universe itself. The light was a messenger not just of distance, but of the changing nature of reality during its journey. The expansion did not occur in isolation. It affected everything from the evolution of stars to the formation of galaxies. Over billions of years, gravity worked against expansion in local regions, pulling matter together into the vast cosmic web we observe today. Clusters, filaments, and voids emerged from what had once been a nearly uniform sea of hydrogen and helium. Yet the large-scale expansion continued unhindered, stretching the distances between these massive structures as time moved forward. By the second half of the 20th century, the expanding universe had become more than a theory. It was a measurable fact. Scientists could determine not only that space was expanding, but also how fast. The rate of expansion, called the Hubble constant, became one of the most important numbers in cosmology. It defined the scale of the universe and its age. Although debates continue about its exact value, the underlying reality it describes is beyond question. The cosmos is growing in scale with every passing second. Still, a quiet confusion remained in the minds of many. The language of expansion naturally invites the question, expanding into what? Even as cosmologists explained that no external space is needed, the human imagination struggles to picture a boundaryless growth. Our senses evolved to navigate finite spaces, to measure distances and volumes, to see edges and centers. The universe defies these instincts. It has no center, no outside, no frontier. The expansion happens everywhere, all at once, within the coordinates of its own geometry. The moment we accept that, our perception of existence itself changes. Space is not an emptiness into which things drift. It is the connective tissue of the cosmos, a dynamic field whose properties shape everything that happens within it. To understand expansion, we must learn to think not of objects moving apart, but of the distances themselves changing. Every galaxy, every atom, every photon exists within this living fabric. It is not space that sits beneath reality. Space is reality. As the 20th century closed, this understanding matured into a unified picture. A cosmos born in expansion, governed by the equations of relativity, filled with galaxies receding in every direction. Humanity had finally begun to grasp the scale and nature of its universe. But the discovery also opened the door to new questions, deeper and stranger than before. If the universe expands as a property of its own geometry, what determines the shape of that geometry? How is space itself curved, and what does that curvature reveal about the ultimate fate of everything? To explore these questions, science had to look beyond the movement of galaxies and into the structure of reality itself. The next step in the journey would lead to the very heart of Einstein's vision, where geometry and existence become one. The universe does not simply exist in space. Space itself is part of what the universe is. This idea, at first abstract and elusive, is the cornerstone of modern physics. It begins with a shift so profound that even today, over a century after it was first proposed, its full meaning continues to unfold. When Albert Einstein presented his theory of general relativity in the year 1915, he rewrote the foundation of how reality is described. In this framework, space and time are woven together into a single entity called space-time. It is not a background or container. It is the fabric of existence itself, capable of bending, stretching, and rippling in response to matter and energy. What we call gravity is not a force pulling through space, but the manifestation of that curvature. The Earth orbits the Sun not because it is tugged by an invisible thread, but because the Sun's mass warps the geometry of space-time, guiding the Earth along a curved path. Imagine space-time as a vast, flexible sheet. Place a heavy object upon it, and the surface curves downward. Smaller objects placed nearby move along the contours of that curve, not because they are pulled directly, but because the shape of the sheet guides their motion. This analogy, though simple, reveals the essence of Einstein's insight. Mass and energy tell space-time how to curve, and space-time tells mass and energy how to move. In this new picture, space is no longer passive. It is dynamic, influenced by the contents of the universe and influencing them in return. This means that as the universe evolves, its geometry changes. Galaxies, stars, and planets move not through a rigid framework, but within a living, flexible structure. The equations of general relativity describe how this geometry behaves, allowing physicists to predict the motion of planets, the bending of light near massive objects, and even the large-scale evolution of the cosmos itself. When applied to the entire universe, Einstein's equations reveal something extraordinary. If space-time is filled with matter and energy, its geometry cannot remain fixed. The equations predict that space must either expand or contract, depending on its total energy content. A perfectly static universe is mathematically unstable. This is what Einstein first resisted, what Hubble later confirmed, and what we now understand as the expansion of space itself. But what does it mean for space to expand? It is a phrase easy to say, but hard to visualize. Expansion is not motion through a void. It is an increase in the distance between points defined by the geometry of space-time. In cosmology, this change is described by a quantity called the scale factor, a number that determines how distances between distant galaxies evolve with time. As the scale factor increases, the universe grows. Galaxies do not travel through space. The space between them stretches. The expansion is encoded in the very metric that defines distance. In everyday life, we assume that the distance between 2 points is fixed unless something physically moves. But on cosmic scales, even if galaxies remain at rest relative to their local surroundings, the overall geometry of space evolves. What we perceive as motion is really the result of changing geometry. This realization forces a deeper appreciation of what space is. It is not emptiness. It has measurable properties, curvature, energy, and even pressure. Space can expand, contract, and carry waves of distortion known as gravitational waves. These ripples, first detected directly in the year 2015, are vibrations in the fabric of space-time itself, created by cataclysmic events like the merging of black holes. They confirm that space is not a static void but an elastic medium capable of transmitting energy across the universe. In the language of physics, space has geometry, and geometry has power. The universe we observe, its expansion, its structure, and even its destiny, is determined by the shape of that geometry. Whether the universe will expand forever, collapse back upon itself, or approach a steady state depends on the balance between energy, matter, and curvature. This was one of the great insights of 20th century cosmology. The fate of the universe is written in its geometry. Yet geometry is not just a mathematical abstraction. It is the very texture of what we call reality. Every second that passes, every meter we measure, is defined by the geometry of space-time. It determines not only where things are, but how they move and how they experience time. Understanding this geometry is the key to understanding expansion itself. The growth of the universe is not something happening within space. It is the evolution of space. Just as a note of music changes as it resonates through air, the universe changes as its geometry evolves through time. This concept can feel distant, but it touches everything we know. The reason light bends when it passes near a star, the reason clocks tick slower in a gravitational field, the reason the universe expands at all of it arises from geometry. Reality is not built upon space and time. Reality is the unfolding of space-time. As this understanding deepened, cosmologists began to realize that the universe's expansion could not be explained as a simple spreading of material. It was a geometric transformation. Every region of space was part of the same structure, and as that structure grew, it carried galaxies apart. The universe was not expanding into emptiness. Emptiness itself was expanding. Yet, if space is dynamic and evolving, what determines its precise shape? Does the universe curve inward like the surface of a sphere, outward like a saddle, or remain perfectly flat? These are not philosophical questions. They are measurable properties, and their answers reveal the ultimate architecture of the cosmos. To explore this, science had to turn its gaze from the local to the infinite, from the behavior of individual galaxies to the geometry of the universe as a whole. And in that geometry lay a new kind of beauty, the realization that the shape of reality itself defines everything we can see and everything we will ever be able to see. The idea that space itself could have a shape was once inconceivable. To ancient thinkers, the cosmos was an orderly construction of spheres, each turning in perfect symmetry. Even in Newton's age, space was thought to be an unchanging stage, infinite, flat, and eternal. But when Einstein showed that geometry and gravity were one and the same, the old certainty dissolved. The universe could bend, curve, or stretch depending on its contents. Reality was not fixed. It was elastic. To understand this geometry, we must first understand that space and time cannot be separated. They form a four-dimensional continuum that behaves as a single entity. What one observer measures as space, another might measure partly as time, depending on their motion. Every event in the universe, the flicker of a star, the orbit of a planet, the passing of a thought, is a point within this four-dimensional fabric. The relationships among these points define the structure of space-time itself. When cosmologists describe expansion, they are not talking about galaxies rushing through pre-existing space. Instead, they describe a change in the scale of space-time. Imagine a grid drawn on a vast rubber sheet. As the sheet stretches, every square on the grid grows, and the distance between any 2 points increases. The points themselves do not move relative to the sheet. The sheet itself expands. In much the same way, galaxies are carried apart by the stretching of space. This expansion follows from the solutions to Einstein's equations known as the Friedmann-Lemaitre-Robertson-Walker models. These describe how the scale factor, the measure of cosmic distance, evolves with time depending on the universe's energy density and curvature. If the universe contains just the right balance of energy, it will be spatially flat. If it contains more, it will curve inward like the surface of a sphere. If it contains less, it will curve outward like a saddle. Each of these possibilities corresponds to a distinct geometry: closed, flat, or open. Geometry, in this sense, is not an abstract concept. It determines how the universe behaves on the largest scales. In a closed universe, parallel lines eventually meet, and if one were to travel far enough in a straight line, one would return to the starting point, just as a traveler on Earth eventually circles the globe. In an open universe, parallel lines diverge forever, and space extends infinitely in all directions. In a flat universe, the geometry obeys the familiar rules of Euclid. Parallel lines never meet, and space extends endlessly without curvature. For much of the 20th century, scientists sought to determine which of these geometries describes our cosmos. The answer required precision measurements of the cosmic microwave background, the faint afterglow of the Big Bang. When satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck mission mapped this ancient radiation, they found something remarkable. The temperature fluctuations across the sky matched almost perfectly what would be expected in a flat universe. The geometry of space, to within a tiny margin of error, is Euclidean. But this result carries a subtle truth. A flat universe does not necessarily mean an infinite one. It could be vast but finite, like the surface of a cylinder, unbounded yet without an edge. The absence of curvature tells us only how space behaves locally, not what lies beyond the observable horizon. Even if the universe were finite, it would still have no edge or center. Every direction would appear the same. every region equivalent. This symmetry is one of the most beautiful features of modern cosmology. The universe has no privileged vantage point. When we say the universe is flat, we are describing the relationship between geometry and energy. In Einstein's equations, curvature is determined by the total density of matter, radiation, and dark energy. If that density equals a precise critical value, the universe is spatially flat. Observations show that our cosmos is astonishingly close to that balance, an equilibrium so delicate it raises deep questions about its origin. Why is the universe so finely tuned that its geometry is nearly perfect? This puzzle points back to the earliest moments after the Big Bang, when the conditions of space were set. Something in those first instants must have smoothed and flattened the universe to the precision we observe today. The answer, scientists believe, lies in a period of extraordinary expansion called cosmic inflation, a fleeting, almost unimaginable event that occurred a fraction of a second after time itself began. Inflation reshaped everything we know about the origin of structure, the uniformity of the cosmos, and the geometry that defines it. To understand why the universe is as flat and homogeneous as it appears, we must travel back to that primordial moment, when space itself swelled faster than light, smoothing every wrinkle in its newborn fabric. In the beginning, before galaxies formed, before light had even scattered freely through space, there was a moment when the universe changed more profoundly than at any time since. It was not an explosion in the ordinary sense. There was no burst of matter into an empty void. It was a transformation of geometry itself, a sudden, breathtaking swelling of space-time. This event is called cosmic inflation. It is one of the most extraordinary ideas in modern cosmology, and one of the few that can explain why the universe looks the way it does today. To grasp inflation, we must look at what happens when energy and geometry interact on the most fundamental level. In the earliest instant of the universe, space was dominated by an intense field of energy, smooth and nearly uniform everywhere. This field, through a process not yet fully understood, acted as a kind of pressure on space-time, causing it to expand exponentially. In a fraction of a second so brief it defies imagination, the universe grew from a region smaller than an atom to something many orders of magnitude larger than the visible cosmos we can observe today. This expansion did not happen within space. It was the expansion of space. Every region of space-time stretched, doubling again and again until all irregularities were ironed out. The curvature flattened. Any tiny unevenness that might have caused the universe to collapse or twist was smoothed away by this tremendous surge. The result was the nearly flat, uniform cosmos that satellites now measure in exquisite detail. During inflation, quantum fluctuations, the minute, random variations that exist in every field, according to the laws of quantum mechanics, were stretched across cosmic scales. What began as subatomic irregularities became the seeds of all structure in the universe. Over billions of years, these tiny variations grew into galaxies, clusters, and the great web of matter that fills the cosmos today. Every star, every planet, every living being traces its origin to those fleeting fluctuations amplified by inflation. When inflation ended, the energy driving it decayed into particles and radiation, filling the universe with the raw material of matter. This was the beginning of what we call the hot Big Bang, not the initial creation of space and time, but the moment when the universe became hot, dense, and filled with energy capable of forming atoms. Light, matter, and geometry began their long, intertwined evolution. The mathematics behind this theory fits perfectly with what we observe. The uniformity of the cosmic microwave background, that faint glow from about 380,000 years after the Big Bang, is precisely what inflation predicts. The slight variations in temperature across the sky, measured by the Planck satellite, match the statistical fingerprint of those ancient quantum fluctuations. The flatness of the universe, the absence of magnetic monopoles, and the vast coherence of its structure all point to the same conclusion. something like inflation must have happened. The idea itself is not simple speculation. It emerges naturally from the equations of quantum field theory and general relativity when applied to the extreme conditions of the early universe. Many versions of inflation exist, differing in detail but sharing the same core principle, that a brief phase of exponential expansion set the stage for everything that followed. Still, inflation challenges intuition. It asks us to imagine space growing faster than light could travel. Yet this does not violate the laws of physics, because nothing moves through space faster than light. It is space itself that expands, carrying everything with it. The speed of light limits motion within space, but it does not limit the stretching of the geometric fabric. As inflation ended, expansion slowed dramatically, but did not stop. The universe continued to grow, cooled, and gradually became transparent to radiation. From this transparency came the first light, which still bathes the cosmos as the microwave background. The structures we see today, galaxies, clusters, and the immense cosmic web, are the echoes of inflation, frozen into the geometry of the universe itself. Through inflation, the cosmos became the vast, nearly flat expanse we observe. It set the initial conditions that allowed stars and galaxies to form, and it provided the framework for every later chapter of cosmic history. Yet, as the universe aged and evolved, another mystery awaited discovery, one that would change our understanding of expansion once again. In the late 20th century, astronomers expected the universe's expansion to slow down under the pull of gravity. But when they looked closely, they found the opposite. The expansion was speeding up. Something was driving space apart with a quiet, relentless pressure. This force was not matter, not radiation, not anything known. It was a property of space itself. This discovery revealed a new cosmic phase, a second era of acceleration that echoes the inflationary surge of the beginning. The universe, it seems, has never stopped expanding. It has simply changed its tempo. When people hear the phrase, "the Big Bang," they often picture an enormous explosion, a cosmic fireball erupting into a pre-existing emptiness, hurling matter outward like fragments from a blast. This image, though vivid, is deeply misleading. The Big Bang was not an explosion in space. It was the expansion of space itself. Nothing burst into a void, because before that moment there was no void, no space, and no time. The universe did not expand into something. It created the very framework in which expansion could occur. In the first moments after inflation ended, the energy that had driven the expansion transformed into particles and radiation. Space was filled with a dense, hot plasma of matter and light, a smooth sea of energy that would gradually cool and condense into the structures we see today. This was the beginning of what we call the Hot Big Bang, a period that followed inflation and defined the observable history of the cosmos. Every point in space was once much closer together, not because all the matter rushed from a single location, but because the entire geometry of space-time was smaller. There was no center, no boundary, no outside region waiting to be filled. Every place in the universe was once part of that same primordial state, and expansion occurred everywhere at once. If one could somehow rewind time, every galaxy would approach every other, not toward a common central point, but simply because the scale of space itself would shrink. To visualize this, imagine the surface of an inflating balloon, dotted with tiny marks. As the balloon expands, each mark moves away from all the others, yet none sits at the center of the expansion. The surface itself grows, and every observer on it sees the same pattern. Neighbors receding, distances increasing, space stretching. Our universe behaves in the same way, except in 3 dimensions of space instead of 2, and without the need for any external air or outside medium. When the universe was only a few 100,000 years old, it had cooled enough for electrons to combine with protons, forming neutral atoms. For the first time, light could travel freely without constant scattering from charged particles. That light, stretched by billions of years of expansion, now fills the cosmos as the cosmic microwave background, a faint afterglow that we can still detect with our instruments. It is the oldest light we can see, a direct image of the universe as it was when it became transparent. The cosmic microwave background is one of the most powerful confirmations of the Big Bang model. It shows that the early universe was remarkably uniform, with only tiny fluctuations in temperature and density, the imprints of quantum variations magnified by inflation. These small irregularities grew over billions of years into galaxies and clusters, forming the large-scale structure that spans the universe today. Yet, the very existence of this uniformity was once a puzzle. How could regions of the sky separated by billions of light-years have nearly the same temperature when there was no time for light or heat to travel between them? Inflation answered this by showing that those regions were once in close contact before the rapid expansion stretched them apart. The horizon problem, as it was called, dissolved once scientists realized that the universe's earliest moments were governed by the stretching of space itself. The Big Bang, then, was not a single flash or detonation. It was the emergence of geometry and energy, intertwined from the beginning. It marked the start of time as we can meaningfully define it. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question assumes a direction that does not exist. Time itself is part of the unfolding, not something that existed before it. Still, the concept of beginning invites wonder. The equations of general relativity trace the universe back to a state of infinite density, a singularity where our current laws of physics break down. But this singularity is not a physical point in space. It is a limit to our understanding, a sign that our theories need a deeper foundation. Quantum gravity, a theory uniting the principles of the very small with those of the very large, may eventually describe what happened at or before that boundary. For now, we can only trace the universe confidently back to the moment when it was a fraction of a second old. What we know for certain is that the Big Bang was the moment space and time began to expand from a hot, dense state. From that instant onward, the universe has evolved in predictable ways. Matter cooled and condensed, stars ignited, galaxies formed, and planets emerged from the remnants of ancient explosions within those stars. Every atom in our bodies was once part of that cosmic fire. We are the cooled ashes of the early universe, arranged into patterns capable of asking how it all began. The misunderstanding of the Big Bang as an outward explosion persists because it is hard to imagine expansion without an outside. But the universe is not expanding into emptiness. Emptiness itself is expanding. Every moment that passes increases the distance between faraway galaxies, not because they are moving through space, but because the space between them grows. The expansion stretches light, lengthens time, and shapes the very structure of reality. When we look into the night sky, we are not seeing stars as they are now. We are looking into time itself, observing light that has traveled for billions of years across a changing universe. The farther we look, the younger the cosmos appears. The deep sky is a time machine, revealing how the universe has evolved from that dense, glowing beginning to the vast web of galaxies we inhabit today. To understand the true meaning of expansion, we must now ask a new question. What is the shape of this universe that has been stretching since the dawn of time? Is it curved upon itself, infinite in extent, or bounded in some hidden way we cannot yet perceive? The next step in our journey is to explore how geometry defines not only what the universe looks like, but also what it can ultimately become. The deeper scientists studied the early universe, the clearer it became that the Big Bang was not a chaotic explosion, but a precisely structured unfolding. Space, time, matter, and energy all emerged in a relationship so elegant that it could be described by a small set of mathematical laws. Yet these laws produced complexity beyond imagination. The simplicity of the beginning gave birth to the richness of everything that followed. In the first few minutes after the Big Bang, the universe was a searing plasma, a storm of protons, neutrons, electrons, and photons colliding in every direction. Temperatures reached billions of degrees, high enough to fuse light elements such as hydrogen, helium, and traces of lithium. This brief period of nuclear synthesis left a signature that astronomers can still measure today in the composition of the cosmos. The abundance of these light elements matches exactly what the Big Bang model predicts. It is one of the strongest pieces of evidence that this event truly marked the origin of our universe's observable history. As expansion continued, the universe cooled. Gravity began to gather matter, and over hundreds of millions of years, small fluctuations in density grew into clouds of gas. Within these clouds, gravity's relentless pull compressed the gas further until nuclear fusion ignited. The first stars were born, immense, short-lived beacons that illuminated a universe still shrouded in darkness. Their light ended what cosmologists call the cosmic dark ages, a time after the universe became transparent, but before stars and galaxies filled it with brilliance. These first stars, far larger than our Sun, burned through their fuel rapidly and died in spectacular explosions called supernovae. In their fiery deaths, they forged heavier elements, carbon, oxygen, iron, scattering them into the surrounding space. Later generations of stars formed from this enriched material, building galaxies and planetary systems. Our own solar system, and everything within it, traces its lineage to those early stars. Every atom in our blood and bones was once part of a star that lived and died billions of years ago. This story, from a smooth plasma to a universe of stars and galaxies, follows directly from the expansion of space. Without expansion, the universe would have collapsed under its own gravity long before life could arise. Without gravity, matter would never have coalesced to form stars at all. It is this delicate balance between expansion and gravity that allowed the cosmos to grow structured but not chaotic, vast but not empty. Yet, for all its elegance, the Big Bang still left many questions. If the universe had a beginning, what determined its initial conditions? Why is it so uniform on large scales but filled with intricate structure on smaller ones? Why is the geometry of space so close to flat? These puzzles pointed beyond the hot Big Bang itself to the inflationary era that preceded it, that tiny fraction of a second when the universe's shape was defined. The Big Bang also revealed a profound truth about time. As the universe expands, it carries the arrow of time with it. Entropy, the measure of disorder, increases as galaxies drift apart and stars exhaust their fuel. Time's direction, from past to future, from simplicity to complexity, is woven into the fabric of cosmic expansion. The universe evolves not because of some external clock, but because expansion itself provides the rhythm. For the human mind, these scales are almost impossible to comprehend. The distances are beyond imagination, the timescales beyond empathy. But the laws that govern them are the same ones that govern the fall of an apple or the orbit of the moon. The unity of these laws, from the smallest particle to the largest cluster of galaxies, is what gives the cosmos its coherence. The Big Bang was not a one-time event that flared and vanished. It is still happening. Every second, every heartbeat, every photon of light participates in that same ongoing expansion. The universe is not expanding away from a single point. It is expanding within itself. The distances between galaxies grow, the wavelengths of ancient light stretch, and time itself flows outward from that primordial moment. Even so, a deep question lingers in both science and philosophy. If the Big Bang marked the beginning of space and time, what lies beyond our horizon of understanding? Is there a deeper reality from which our universe emerged? A greater space-time, a multiverse, or something entirely different? For now, such ideas remain speculation. The evidence we can measure tells us only what happened within our own cosmic horizon. Beyond that, the equations continue, but the data end. In the pursuit of understanding, scientists have learned to distinguish between what is knowable and what lies beyond current observation. The Big Bang belongs to the knowable realm. Its traces are everywhere. In the cosmic microwave background, in the ratios of light elements, in the expansion of distant galaxies. Together, these clues form a consistent story that stretches back nearly 14 billion years. The more we learn, the more the question changes. Instead of asking what caused the Big Bang, we begin to ask what shape does this expanding universe take? If the Big Bang was the beginning of space, then the geometry of that space determines everything. How light travels, how time flows, and whether the universe will expand forever or someday fall back upon itself. The answers to these questions lie not in explosions or beginnings, but in the quiet, precise geometry of the cosmos. And so, the journey turns from the birth of space to the shape of space, the grand architecture upon which the entire story unfolds. As the universe expanded and cooled, its vast geometry began to reveal itself. What had once been a dense, glowing fog of energy transformed into a transparent sea of light and matter. Across billions of light years, the young cosmos carried the faint memory of its earliest form, a pattern of tiny fluctuations frozen into the cosmic microwave background. These ripples are not random. They are the faint fingerprints of the universe's geometry written across the sky. By studying these patterns, cosmologists learned how to measure the shape of the universe itself. The question they sought to answer was deceptively simple. Is space curved or is it flat? In everyday experience, flatness and curvature seem obvious. A table is flat, a globe is curved. But in the language of general relativity, curvature is not just a shape we see. It is a property of space-time itself, determined by how energy and matter are distributed throughout the cosmos. To measure that curvature, scientists look to the relic light of the Big Bang. Tiny temperature variations in the cosmic microwave background act like dots on an enormous cosmic map. If the universe were curved inward, like the surface of a sphere, those dots would appear larger than expected. If it were curved outward, like a saddle, they would appear smaller. By comparing observations to predictions, astronomers could determine the geometry of space with extraordinary precision. The results, drawn from missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite, revealed a striking truth. On the largest observable scales, the universe is flat to within a fraction of a percent. The cosmic triangles, shapes formed by tracing light paths across vast distances, obey Euclid's familiar rules. Parallel lines never meet, and the angles of a large triangle add up to 180 degrees. In the vast arena of the cosmos, geometry behaves as though space extends endlessly without curvature. Yet, flatness does not necessarily mean infinity. The universe could be finite but unbounded, much like the surface of a cylinder or torus, a shape that closes in on itself without an edge. To an observer within it, space would appear uniform and endless in all directions. This concept defies ordinary intuition because it suggests a cosmos without a center or boundary. Every point is equivalent, every direction infinite from a local perspective. In this view, there is no edge to fall off, no outer rim where the universe ends and emptiness begins. The universe may curve back upon itself in ways we cannot directly perceive because the observable horizon limits what we can see. Beyond that horizon, space continues, perhaps repeating, perhaps stretching infinitely, perhaps connecting in ways our measurements cannot yet reveal. The discovery of cosmic flatness deepened another mystery. The balance between expansion and gravity that defines this flatness is incredibly delicate. If the density of matter and energy in the early universe had been slightly greater, space would have curved inward and eventually collapsed. If it had been slightly less, it would have curved outward and expanded too quickly for galaxies and stars to form. The observed near-perfect flatness means that the universe's initial conditions, were tuned to an astonishing precision. Inflation, with its exponential stretching of space, offers the most compelling explanation for how that balance was achieved. Flat geometry also affects the universe's fate. In a closed cosmos, expansion might one day reverse, leading to a collapse known as the Big Crunch. In an open or flat universe, expansion continues indefinitely. The rate of that expansion depends not only on matter and radiation, but also on something far more mysterious, a form of energy intrinsic to space itself. This energy, invisible yet dominant, is known as dark energy. The realization that dark energy governs the expansion of the universe marks one of the greatest scientific discoveries of modern times. It reshaped our understanding of the cosmos just as deeply as Hubble's revelation of expansion did nearly a century earlier. The same equations that describe the geometry of space now hint that this invisible energy permeates it, driving its growth faster with time. This quiet acceleration, measured in the light of distant supernovae, tells us that the universe's expansion is not slowing down under gravity's pull. Instead, it is speeding up. The same space-time fabric that once swelled in inflation's first breath now stretches again, gently but relentlessly, across billions of light years. The geometry of the cosmos, once thought to be static, is still evolving. Space itself is not a fixed canvas, but a living entity that grows, expands, and reshapes its own curvature. Every beam of light that reaches us carries within it the story of that geometry, a record of how reality has stretched since the moment it began. In this way, the universe tells its story not through explosions or collisions, but through the slow, majestic expansion of space itself. Geometry is destiny. The way space curves and stretches decides how galaxies move, how time flows, and ultimately how the cosmos will end. And so, as we trace the shape of the universe, we are also tracing its past and its future. From the gentle hum of the microwave background to the accelerating flight of distant galaxies, the evidence speaks with one voice. The universe expands not into something else, but within itself, guided by the silent laws of its own geometry. What began as a question about light and distance has become an exploration of reality's foundation. To understand why the universe expands and what drives it now, we must look beyond curvature alone. The next step leads us into the age of acceleration, a time when dark energy began to dominate the cosmos, changing not only its pace, but its destiny. When we look out into the deep sky, we are not just seeing stars. We are looking into the shape of reality itself. Every photon of light that reaches us has followed the invisible curves and contours of space-time, tracing paths sculpted by the geometry of the cosmos. The way those paths bend, the way distances stretch, and the way time itself flows all depend on a single question. What is the shape of the universe? Einstein's equations allow for three broad possibilities. The universe could be closed, like the surface of a sphere. It could be open, like the shape of a saddle. Or it could be flat, extending endlessly with no curvature at all. Each geometry carries a distinct destiny. In a closed universe, expansion would one day slow and reverse, leading to a collapse, a big crunch that mirrors the Big Bang in reverse. In an open or flat universe, expansion would continue forever, growing slower or faster depending on how much energy space contains. To test these ideas, astronomers turned to the oldest light in existence, the cosmic microwave background. When this light was released, the universe was only a few 100,000 years old. It has been traveling through space ever since, its wavelength stretched by cosmic expansion until it now glows in the microwave range. Encoded within its faint variations are the clues to the universe's curvature. The Planck satellite, launched by the European Space Agency, mapped this background in exquisite detail. Its data showed that the temperature fluctuations across the sky have a very specific size pattern, one that matches what we would expect in a flat universe. If space were curved inward or outward, those patterns would appear distorted. But they do not. The geometry of the universe is flat to within less than 1%. A flat universe does not necessarily mean infinite. It can also mean unbounded. The surface of a sphere, though finite, has no edge. You can travel around it endlessly without ever encountering a boundary. In the same way, the three-dimensional universe could be vast yet self-contained, wrapping around on scales so immense that light itself has not had time to complete a circuit. To inhabitants within it, every direction would appear infinite. There would be no center, no outside, and no end. This concept is difficult for the human mind to grasp because our intuition is built from a world of surfaces and boundaries. We imagine edges because everything we experience has limits. Oceans meet shores, air meets walls, planets orbit within space. But the universe as a whole does not exist inside something larger. Space is not a container. It is the thing being described. When we speak of the universe expanding, we are not describing motion through a void. We are describing the stretching of the void itself. The geometry of space is determined by its contents. Matter and energy curve space-time, and the balance between density and expansion determines whether the universe is open, flat, or closed. For decades, cosmologists have measured this balance through a quantity known as the critical density, the amount of energy required for space to be perfectly flat. The combined contributions of ordinary matter, and dark energy together appear to meet this critical value almost exactly. The universe is balanced on the edge between openness and closure, a cosmic equilibrium that hints at something deeper in its earliest moments. This near-perfect balance might seem improbable, but inflation explains it naturally. During that brief epoch of rapid expansion, any initial curvature was stretched to near flatness, much like the surface of an inflating balloon appears flatter as it grows larger. Inflation smoothed the wrinkles of the young universe, setting the stage for the geometry we see today. If the universe is indeed flat, its expansion may never end. Distant galaxies will continue to recede, their light stretching into ever longer wavelengths until it fades beyond visibility. Over unimaginable timescales, the cosmos will grow dark and cold, its energy spread thin across expanding space. Yet within this quiet future lies a profound truth. The same laws that predict the universe's end also reveal its beauty. The geometry that allows the universe to expand forever is the same geometry that allowed stars, planets, and life to exist at all. Still, small uncertainties remain. Measurements of the cosmic microwave background, of the distribution of galaxies, and of gravitational lensing, the bending of light by mass, all point to near flatness, but not with absolute finality. The universe could be slightly curved, either closed or open, on scales beyond our current ability to measure. If it is closed, space might one day wrap back on itself in ways that would cause light to meet itself after billions of years of travel. If it is open, it may stretch into infinity, forever expanding and thinning. What we can say with confidence is that the observable universe, the region from which light has had time to reach us, forms a sphere roughly 92 billion light-years across. Beyond that sphere, the universe continues, perhaps infinitely, perhaps looping back in ways beyond perception. The term observable reminds us that our view is limited by light and time, not by any physical boundary. There may be far more universe than we can ever see, hidden beyond the horizon of visibility. The shape of the universe is not only a question of geometry, but also of destiny. If space is flat and expansion accelerates under the influence of dark energy, the cosmos may expand forever, growing emptier as time stretches onward. Galaxies will drift beyond one another's reach, stars will burn out, and only the faint glow of radiation will remain. This distant future, sometimes called the heat death, is not a collapse, but a fading, a slow quieting of cosmic motion as everything spreads beyond interaction. To know the shape of the universe, then, is to know the story of its past, and the outline of its future. From the first flicker of inflation to the faint hum of cosmic acceleration, geometry has guided every moment. The cosmos is not expanding into something else, it is expanding as itself, an unbounded, ever-evolving structure of space and time. And yet, a deeper mystery remains. What set this geometry in motion? What caused the initial burst of expansion that shaped everything that followed? To answer that, we must look back to the briefest and most dramatic era of all, the moment when inflation began and the seeds of every galaxy were sown. During the first instant of existence, the universe was not simply filled with matter and light, it was filled with potential. The geometry that defines everything today was not yet settled. The balance between expansion and gravity, between density and curvature, hung in an unstable equilibrium. Then, in a heartbeat of cosmic time, something extraordinary happened. Space itself underwent an explosive transformation, expanding far faster than at any other period in its history. This brief but defining moment is known as cosmic inflation. Inflation began when the universe was unimaginably young, far less than a trillionth of a second old. At that time, the energy of the universe was concentrated in a field that permeated all of space-time. Physicists call it the inflaton field, though its exact nature remains unknown. What matters is that this field carried with it an immense potential energy, a kind of pressure that drove the universe to expand exponentially. In that fleeting instant, space grew by factors so vast that distances smaller than atoms became stretched to cosmic scales. The effect was transformative. Any initial curvature that might have existed was smoothed out, much like wrinkles disappearing as a balloon expands. Regions of the universe that had been in close contact were suddenly separated beyond communication, explaining why the cosmos looks so uniform across enormous distances. Inflation solved the horizon problem, the question of why the universe appears the same temperature everywhere, even in regions that could never have exchanged light or heat. It also explained the flatness problem, the fine balance between expansion and gravity that would otherwise seem an improbable coincidence. Yet, inflation did more than flatten and smooth the universe. It planted the seeds of everything we see. Quantum mechanics tells us that even empty space is never perfectly uniform. Tiny fluctuations constantly arise, flickering into and out of existence. During inflation, these microscopic variations were stretched to astronomical scales. The minute differences in energy density became the faint ripples that, billions of years later, would form galaxies, stars, and planets. The structure of the entire cosmos traces its origins to those fleeting quantum fluctuations in the first breath of time. When inflation ended, its driving energy was released into the universe, reheating it in a burst of radiation and particles. This marked the beginning of the hot Big Bang phase, the era when matter and light filled space, and the cosmos began the slow, steady expansion that continues to this day. From that point forward, the universe evolved according to well-understood physics. The dramatic acceleration of inflation gave way to a more gradual expansion governed by gravity, radiation, and matter. The evidence for inflation is written across the sky. The cosmic microwave background, the ancient light from when the universe was less than 400,000 years old, bears the imprint of those primordial fluctuations. Their pattern, random but statistically balanced, matches the predictions of inflation with remarkable precision. The large-scale distribution of galaxies, too, follows the same pattern. The universe is a scaled-up echo of quantum noise from its earliest moments. Some theories suggest that inflation might never have ended completely. In certain regions of space-time, the inflaton field could continue to expand indefinitely, spawning new universes within an ever-growing multiverse. Each pocket of this cosmic foam would have its own physical constants, its own geometry, perhaps even its own version of time. While this idea remains speculative, it reveals how far-reaching the implications of inflation can be. The physics that shaped our universe may be part of a grander cosmic process, that extends far beyond what we can observe. Still, even without invoking other universes, inflation alone explains nearly every major feature of the cosmos we inhabit. It tells us why the sky looks the same in every direction, why the geometry is flat, and why galaxies formed from faint ripples rather than chaos. It bridges the gap between the quantum world of the very small and the cosmic world of the very large, two domains that seem utterly different, but are, in truth, linked by geometry and energy. Inflation reminds us that the universe we see today, vast, stable, and structured, was born from an instant of unimaginable violence and simplicity. It shows that even the calm, predictable patterns of galaxies are the frozen echoes of quantum chance. The cosmos, in its grandeur, carries within it the signature of the microscopic. When inflation ended, the universe entered a new era, one dominated by matter and light. Gravity began to gather matter into clumps, forming the first stars and galaxies. For billions of years, expansion slowed as gravity tried to pull everything back together. The battle between expansion and attraction shaped the evolution of the cosmos. But the balance would not last forever. In the late 20th century, astronomers discovered that something unexpected was happening. The universe's expansion, instead of slowing down, was speeding up. Some mysterious energy, woven into the fabric of space, itself was driving galaxies apart faster than gravity could resist. This new discovery echoed the same kind of acceleration that had once occurred during inflation, a quiet, persistent version of that first cosmic surge. The universe, it seemed, had entered a second age of acceleration. And just as before, the key to understanding it lay in the geometry of space and the energy it contains. As the universe aged, its expansion did not stop. For billions of years after the Big Bang, gravity held the upper hand. Galaxies drew together in clusters, stars formed from collapsing clouds of gas, and matter shaped the large-scale structure of the cosmos. Expansion continued, but it slowed under gravity's pull. It seemed natural to assume that this deceleration would persist forever, that the universe would either expand at a steadily decreasing rate or, if dense enough, eventually collapse back into itself. But at the close of the 20th century, a quiet revolution began. Two independent teams of astronomers, studying the light of distant stellar explosions known as Type Ia supernovae, found something no one had predicted. These supernovae, which serve as cosmic beacons because of their consistent brightness, appeared dimmer than expected. The implication was staggering. The galaxies hosting them were farther away than they should have been if the expansion were slowing. The universe's expansion was not decelerating at all. It was accelerating. The discovery, announced in 1998, transformed cosmology. The data could not be explained by any known form of matter or energy. Gravity, which only attracts, could not produce acceleration. Something else had to be at work. A mysterious energy inherent to space itself, a property that causes space-time to stretch faster as it grows. Scientists called it dark energy. This was not an entirely new idea. Decades earlier, Einstein had introduced the cosmological constant, a term in his equations that acted as a repulsive form of gravity. He had added it reluctantly to maintain a static universe and later discarded it after Hubble's discovery of expansion. But the accelerating universe revived Einstein's abandoned term, now interpreted in a new light. The cosmological constant could represent an energy density of empty space, not matter, not radiation, but the energy of the vacuum itself. Dark energy is now understood to make up about 70% of the total energy content of the cosmos. It does not clump or gather like matter. It does not glow or absorb light. Instead, it acts uniformly throughout space, pushing the expansion of the universe faster with time. Its nature remains one of the greatest unsolved mysteries in science. Whether it is truly constant, as Einstein's term implies, or slowly changing, as other theories suggest, we do not yet know. but its effects are undeniable. The discovery of dark energy forced scientists to rethink the fate of the cosmos. If this repulsive energy continues to dominate, the universe will keep expanding forever, its galaxies drifting ever farther apart until their light can no longer reach one another. The night sky of the far future will grow empty as the nearest galaxies fade beyond the cosmic horizon. Stars will die, new ones will cease to form, and what remains will be an ocean of cold, dark space, the slow heat death of a universe that never stops expanding. Yet even this bleak future carries profound beauty. It shows that space itself is not a passive stage, but a living component of the cosmos, capable of storing energy, driving motion, and shaping destiny. Expansion is not something that happens in space. It is something that happens to space. The same geometry that governs the orbits of planets and the bending of light also determines how the entire universe evolves with time. Dark energy, though invisible, leaves its signature everywhere. It stretches the light from distant galaxies, alters the growth of cosmic structure, and shifts the delicate patterns in the cosmic microwave background. By measuring these effects, scientists can track how the universe's expansion has changed through history. The data reveal a story written across billions of years, a story in which geometry and energy are forever entwined. The acceleration does not tear galaxies or solar systems apart. Its influence becomes noticeable only on the largest scales, between clusters of galaxies separated by hundreds of millions of light years. Within galaxies, gravity remains strong enough to bind stars and planets together. But across the cosmic web, dark energy rules. It is the silent rhythm beneath all existence, the unseen hand that guides the universe toward its distant future. Some physicists speculate that dark energy might not be constant at all. Perhaps it evolves slowly over time, driven by a hidden field that pervades the cosmos, similar to the one that fueled inflation in the first instant of creation. If so, then the universe could one day change its behavior once more, speeding up faster, slowing down, or even reversing into collapse. These ideas remain uncertain, but they remind us that the cosmos is not static or final. It is an evolving story still being written in light and geometry. In the grand arc of cosmic history, two great accelerations frame everything: inflation at the beginning and dark energy at the present. Both involve space expanding not into something else, but within itself. Both arise not from forces acting upon space, but from the properties of space itself. The same universe that once surged outward in a violent burst now continues its expansion in a quiet, persistent drift, guided by the same fundamental laws. The realization that the universe expands ever faster invites a final question, one that has haunted cosmology from its earliest days. If the universe is expanding, and if this expansion is accelerating, does it have a boundary? Is there an edge beyond which nothing exists? Or does space extend without limit, forever beyond our ability to see? To find that answer, we must explore the concept of the observable universe, the part of reality that light and time allow us to perceive. Beyond that horizon lies the great unknown, where space continues to expand beyond our reach. The universe we observe today, with its galaxies, stars, planets, and immense voids, was not always so intricate. In its earliest moments, after the end of cosmic inflation, everything was nearly uniform. Space was filled with a smooth sea of energy, almost identical in every direction. Yet within that smoothness lay the tiniest imperfections, fluctuations in density so small that they seemed meaningless at first. Over billions of years, those minute differences became everything. They were the seeds from which the entire cosmic structure would grow. To understand how this happened, we must return to the fleeting instant when inflation ended. The energy that had driven the universe's rapid expansion decayed into a vast ocean of radiation and particles, filling space with heat and light. the universe became dense and hot, a newborn cosmos expanding and cooling with time. In this turbulent environment, quantum fluctuations from the inflationary period were imprinted onto the fabric of space-time itself. These slight variations, random and minute, meant that some regions were just a little denser than others. Gravity began to amplify those differences. Regions that were denser pulled in more matter, growing ever denser in a self-reinforcing cycle. Over millions of years, gas collected into filaments and clumps. As these clumps collapsed further under their own gravity, they ignited into stars. Groups of stars became galaxies, and galaxies gathered into clusters connected by vast threads of matter. From the smallest quantum tremors came the immense cosmic web, a structure spanning billions of light years, intricate yet born from simplicity. The cosmic microwave background provides a snapshot of this process in its infancy. When the universe was only a few 100,000 years old, it was filled with a hot plasma of electrons, protons, and photons locked together in a constant dance of scattering. As the universe expanded and cooled, these particles combined into neutral atoms, allowing light to travel freely for the first time. The faint temperature variations visible in that ancient light correspond exactly to the tiny density fluctuations predicted by inflation. They are the blueprints of every galaxy that would later form. Inflation explains not only the uniformity of the cosmos, but also its structure. Without inflation, it would be nearly impossible for the universe to look as it does. The horizon problem, the flatness problem, and the origin of large-scale structure all find their resolution in this single event. The universe we see, smooth on the larger scales but filled with intricate patterns on smaller ones, is precisely what inflation predicts. Yet, while the evidence for inflation is strong, its underlying mechanism remains mysterious. Physicists can describe how it behaved, but not exactly why it occurred or what caused it to stop. The field that drove inflation might be connected to deeper laws of quantum, gravity, or to new forms of physics that lie beyond our current understanding. What we can say is that inflation set the initial conditions for everything that followed. It determined the shape, size, and composition of the cosmos. As the universe expanded and cooled, new forces emerged, and the first atoms formed. Hydrogen and helium, the simplest elements, became the raw material for future stars. Within those stars, nuclear fusion would create heavier elements, carbon, oxygen, and iron, building the ingredients for planets, and eventually, for life. All of this was encoded in the faint ripples of the early universe, shaped by inflation's grand sweep. When we observe galaxies across billions of light years, we are seeing those ripples made visible. Each galaxy is a frozen wave in the sea of space-time, a crest formed by density variations that began as quantum fluctuations. The patterns in their distribution, the clustering of matter, and the great voids between them are direct consequences of that inflationary beginning. The universe, in its complexity, is the amplified whisper of quantum noise. Inflation also carries a philosophical weight. It suggests that the entire observable universe, everything we can ever see, emerged from a region once smaller than an atom. The scale difference is beyond imagination. What we call the universe may be just a tiny patch of a far larger whole, stretched beyond the limits of observation. Inflation, if it occurred as the equations describe, could mean that our visible cosmos is but one fragment of a vast and possibly infinite structure, still expanding in ways we can never measure. The story of inflation is also a story of balance. It shows that the universe began in simplicity, governed by a few fundamental laws, and that from that simplicity emerged the complexity of stars and life. The geometry of space, the strength of gravity, the uniformity of temperature, all trace back to the briefest moment of expansion. The seeds of structure were sown not by chaos, but by the quiet precision of physics unfolding at its most fundamental scale. Yet inflation alone does not define the present universe. The expansion that began then continues even now. though at a vastly slower pace. For billions of years, matter and gravity shaped the cosmos. But as it grew larger and older, another form of expansion began to dominate, one not driven by the violent burst of the early universe, but by something subtler, a quiet force woven into space itself. This new expansion, discovered in our own time, mirrors the inflationary moment that began it all. It is driven not by quantum fields of the early universe, but by dark energy, the mysterious property of space that causes it to accelerate once again. In this symmetry of beginnings and endings, the universe tells a single continuous story, from a moment of blazing creation to a slow, inevitable drift into emptiness. To understand what this means for the cosmos today and for its ultimate fate, we must follow this expansion forward into the age of acceleration, where geometry, energy, and time all converge to reveal the universe's quiet future. When inflation ended and the young universe entered its slower phase of expansion, time began to move in a way that could be measured. From that moment, the laws of physics as we know them took control. Gravity began gathering matter into vast clouds of gas, while the background radiation from the early fireball slowly cooled. The universe entered its long period of construction, the making of structure out of near-perfect uniformity. The faint fluctuations seeded by inflation were unimaginably small, differences of only 1 part in 100,000. Yet, gravity is relentless. Over millions of years, these tiny irregularities grew. Denser regions drew in more matter, their gravitational pull strengthening as they grew heavier. Over hundreds of millions of years, the once smooth universe developed texture, a pattern of filaments, nodes, and voids that would one day form the great cosmic web. Within these filaments, hydrogen gas began to collapse under its own weight. The first stars flared into existence, flooding the darkness with light. They lived brief, brilliant lives, burning their fuel rapidly before dying in titanic explosions. These first supernovae scattered heavier elements across space: carbon, oxygen, and iron, the ingredients that would later form planets and living beings. The light from those early stars, redshifted by expansion, still travels toward us, carrying with it the story of how the universe awakened from darkness. This era, the age of structure formation, connected the microscopic with the cosmic. The random quantum variations of inflation became the scaffolding upon which galaxies were built. Modern telescopes, mapping the large-scale distribution of galaxies, reveal a pattern that matches those early fluctuations almost perfectly. On the grandest scales, the universe resembles a network of luminous threads spanning hundreds of millions of light years, each strand marking regions of slightly higher density from the universe's earliest days. Between these filaments lie enormous voids, regions where matter is scarce and expansion proceeds unimpeded. The existence of these vast cosmic bubbles demonstrates how expansion and gravity interact. Where matter is dense, gravity slows expansion, pulling structures together. Where matter is thin, expansion dominates, and space stretches more freely. The balance between these two effects gives the universe its intricate architecture. The remarkable part of this story is that it can all be traced back to physics we understand. From the smooth glow of the cosmic microwave background to the clustering of galaxies today, every observation supports a single coherent picture. The same equations that describe the motion of planets and the bending of light also describe the evolution of the entire cosmos. This unity of scale, from the atomic to the astronomical, is one of the triumphs of modern science. Inflation did more than explain the structure we see. It also linked the two great domains of physics, the quantum world and the relativistic cosmos. It showed that the randomness inherent in quantum mechanics, when magnified by cosmic expansion, could produce the order of galaxies and stars. The ripples in space-time that inflation left behind, faint gravitational waves, may still echo through the universe today. scientists are searching for their imprint in the polarization of the cosmic microwave background, hoping to glimpse the signature of those first moments. If detected, these primordial gravitational waves would offer direct evidence of inflation and a bridge between the smallest and largest scales of reality. They would confirm that quantum mechanics does not merely govern the microscopic, but helped shape the very structure of existence. It is a vision of nature that is both humbling and unifying. The random fluctuations of the quantum vacuum giving rise to everything we see, from galaxies to life. Still, there are mysteries that inflation leaves unsolved. It describes how the universe expanded, but not why inflation began or what caused it to end. Some theories suggest it might have been triggered by transitions in energy fields. Others propose that it never fully stopped, that beyond our cosmic horizon, new universes continue to form in an endless cycle. These ideas remain beyond current observation, but they remind us that inflation may be only one chapter in a larger cosmic story. As the early universe settled into its slower expansion, gravity continued its work. Galaxies merged, stars formed, and cosmic structure matured. Billions of years later, our own sun was born in the spiral arms of the Milky Way, surrounded by the dust and gas that would form the planets. The atoms in our bodies, forged in the hearts of earlier stars, became part of a world capable of looking back and asking how it all began. Through inflation, the universe gained its vastness. Through gravity, it gained its structure. Through time, it gained memory. The cosmos that surrounds us is both ancient and alive with motion, still shaped by the same forces that sculpted its beginning. Expansion continues, but the pattern of galaxies, filaments, and voids remains the quiet imprint of that first burst of creation. Now, billions of years later, the universe finds itself in a new and mysterious phase. Just as inflation drove its birth, something else now drives its continued acceleration. A force equally profound, equally silent, and perhaps equally fundamental. To understand it, we must leave the early universe behind and step into the modern age of cosmic expansion, an era defined not by fire and quantum energy, but by emptiness itself. For most of cosmic history, gravity was the sculptor of everything. It gathered gas into galaxies, stars into clusters, and clusters into filaments that stretched across the cosmic web. The universe expanded, yes, but the expansion slowed with time as matter pulled against it. Scientists once believed that this tug of gravity would continue forever, that the universe would gradually decelerate, perhaps even reverse into collapse. Yet, at the close of the 20th century, the cosmos revealed a secret that overturned that expectation. In 1998, two teams of astronomers observed a series of distant Type Ia supernovae, brilliant stellar explosions that shine with predictable brightness. By comparing their apparent brightness to their known intrinsic luminosity, astronomers could measure distances across billions of light years. What they found was astonishing. The light from these ancient explosions was dimmer than expected, suggesting that the galaxies containing them were farther away than models predicted. The only explanation was that the universe's expansion was speeding up, not slowing down. This quiet revelation marked one of the most profound discoveries in science. The cosmos was not just expanding, it was accelerating. Something unknown was driving space to stretch faster and faster with time. Gravity, which pulls matter together, could not account for this. Whatever was at work must push outward, counteracting gravity on the largest scales. Scientists named it dark energy. Dark energy is unlike anything else we know. It does not form stars, planets, or galaxies. It does not clump or emit light. It seems to exist uniformly throughout space, affecting the geometry of the universe as a whole. Its discovery revived an idea Einstein had introduced 8 decades earlier, the cosmological constant, a term he added to his equations of general relativity to balance gravity and keep the universe static. When Hubble revealed that the universe was expanding, Einstein removed it, calling it his greatest mistake. Yet the acceleration discovered in 1998 brought that mistake back to life, now interpreted not as an error, but as a clue. If the cosmological constant represents the energy of empty space itself, then even a vacuum has weight, or more precisely, an effect on geometry. This vacuum energy does not dilute as the universe expands. Instead, it remains constant per unit of volume, so as space grows, its total energy increases. The result is a steady pressure that accelerates expansion. Space, it seems, carries within it a built-in engine of repulsion. Today, dark energy is thought to make up nearly 70% of the total energy content of the universe. Dark matter accounts for roughly 25%, and ordinary matter, everything we can see, touch, and measure, less than 5%. The cosmos is thus dominated by two invisible ingredients, one that holds galaxies together and another that drives them apart. It is a delicate balance of attraction and expansion, shaping the universe's fate. The discovery of dark energy also transformed our understanding of cosmic geometry. The same observations that revealed acceleration confirmed that the universe is remarkably flat, a balance between the density of matter and the repulsive energy of the vacuum. In Einstein's equations, geometry and energy are inseparable. The universe's flatness tells us that the total energy density is almost exactly the critical value required for equilibrium. But within that balance lies a paradox. How can so much of the cosmos consist of something we cannot detect directly? Attempts to explain dark energy have led to theories both subtle and profound. Some physicists view it as the cosmological constant, a fixed property of space, unchanging through time. Others propose that it is dynamic, driven by a field that slowly evolves as the universe ages. Such models, often called quintessence, suggest that the acceleration might not continue forever. It could change or even reverse, depending on the properties of that hidden field. But for now, all observations indicate that dark energy behaves like a constant pressure, uniform, silent, and relentless. Its effects are visible in the way galaxies move. On small scales, gravity dominates, holding galaxies and clusters together. On the largest scales, dark energy takes over, pushing clusters apart faster than gravity can pull them back. The cosmic web stretches, its filaments thinning as the universe's expansion accelerates. Distant galaxies drift beyond our horizon, their light stretched into oblivion by the growing fabric of space. The idea that space itself can possess energy challenges intuition. For centuries, scientists imagined the vacuum as nothingness, an absence of matter, energy, and motion. But quantum physics revealed that emptiness is never truly empty. Even in perfect vacuum, fields fluctuate, particles appear and vanish, and virtual energy permeates the void. Dark energy may be the large-scale manifestation of this quantum restlessness, the quiet hum of the universe's ground state, magnified across cosmic distances. If dark energy continues to dominate, the future of the universe is already written. Expansion will proceed endlessly, and every distant galaxy not bound to ours by gravity will drift away beyond reach. In the far future, billions of years from now, observers in our own galaxy, if any still exist, will see only darkness beyond the local stars. The cosmic microwave background will fade below detectability, and even the memory of other galaxies will vanish from sight. The universe will appear static once again, not because it has stopped expanding, but because everything beyond has moved forever out of view. This cosmic loneliness is the destiny implied by dark energy. Yet within it lies a poetic symmetry. The same universe that began with a burst of rapid inflation ends with another, slower acceleration. The first expansion created structure, the second dissolves it. Both arise not from motion through space, but from the evolution of space itself. The age of acceleration reminds us that space is not a void. It is a physical entity, a participant in the story of creation. It can stretch, it can carry energy, and it can determine the fate of everything within it. The galaxies we see are not moving through an external backdrop. They are being carried apart by the expansion of that backdrop. The cosmos grows not into something else, but within its own geometry. To grasp the full meaning of this, we must now confront the boundaries of perception itself, the limits of what we can observe. The universe may extend far beyond the region we can ever see, and the expansion ensures that those unseen regions will remain forever hidden. To understand the true scope of reality, we must explore the concept of the observable universe, the sphere of space and time from which light has had time to reach us since the beginning. As astronomers refined their measurements through the early 21st century, the picture of an accelerating universe grew clearer and stranger. Every telescope that peered deep into space found the same message written in the light of ancient galaxies. The universe is not only expanding, it is doing so faster with time. The acceleration is gentle but inexorable, and because it acts everywhere at once, there is no fixed point of origin, no center, no edge, just space itself, quietly stretching. This expansion is not something we can see directly, because it unfolds across billions of light years. Within our own galaxy, and even within clusters of galaxies, gravity remains strong enough to bind matter together. The stars do not drift apart. The solar system does not stretch. What accelerates is the immense emptiness between galaxies, the cosmic ocean in which everything floats. Over cosmic time, that ocean grows deeper and broader, carrying islands of matter farther and farther apart. Scientists describe this mathematically through the scale factor, a measure of how distances between non-gravitationally bound objects change with time. The derivative of that scale factor gives the rate of expansion, known as the Hubble parameter. Observations from supernovae, the cosmic microwave background, and large-scale structure all point to the same trend. The scale factor is increasing at an accelerating rate. This means that the separation between galaxies not bound together will double, then redouble, again and again, with no sign of reversal. The light from those distant galaxies tells a story that is both scientific and poetic. As space expands, the wavelengths of light traveling through it stretch. What began as brilliant blue or white light from a young galaxy becomes deep red after billions of years of travel. For galaxies far enough away, the light is stretched so much that it slips beyond visibility, fading into infrared and radio waves before disappearing entirely. This redshift is not a Doppler effect caused by motion through space. It is the result of the fabric of space itself expanding as the light moves through it. The photon does not lose energy to friction or resistance. It simply becomes longer, its rhythm slowed by the growing geometry of the universe. Over immense timescales, this stretching of light will lead to a kind of cosmic silence. Distant galaxies will recede faster than light can reach us, not because they are moving through space faster than light, relativity forbids that, but because the space between us expands faster than light can cross it. They will fade beyond the cosmic horizon, leaving only the local group of galaxies bound together by gravity, the Milky Way, Andromeda, and a few smaller companions merging into a single island of stars adrift in an ever-widening sea. For observers in that distant future, the evidence of cosmic expansion will vanish. The microwave background will cool until its faint glow disappears entirely, and the sky will seem static once again. Without visible galaxies beyond their own, those future astronomers, if any remain, would have no way to know that their universe was once filled with countless galaxies, all rushing away into darkness. They would see only their local stars, unaware that an entire cosmic history had unfolded before them. This vision of the far future is not just melancholy, it is deeply revealing. It shows that the universe is not timeless, it evolves, and its expansion defines the direction of that evolution. What we call now is a brief window in which the cosmos is both visible and comprehensible. We live at a moment when the sky still holds the memory of its origins. when the afterglow of the Big Bang can still be seen, when galaxies still fill the heavens. In cosmic terms, this is a privileged moment, fleeting and rare. Dark energy ensures that this moment will not last. As the universe continues to accelerate, time and distance will lose their familiar relationship. The cosmic horizon, the maximum distance from which light can ever reach us, will shrink in relative terms, enclosing a smaller and smaller portion of the total universe. Beyond it, space will keep expanding, and whatever lies there will be forever beyond our knowing. Some physicists call this ultimate state the cosmic event horizon. It is not a physical wall, but a boundary in time, a limit to causality. Beyond it, events can occur, but their light will never reach us, no matter how long we wait. The universe, infinite in possibility, will become finite in perception. This is not just a horizon of light, but a horizon of knowledge. It marks the boundary between what can be known and what can never be known. In this expanding future, the universe will continue to cool, stars will burn out, galaxies will dim, and matter itself will, slowly, disintegrate. Over unimaginable timescales, black holes will evaporate through Hawking radiation, releasing their energy into an ever-thinning cosmos. In the end, only faint whispers of radiation will remain, stretched into wavelengths so long that they will never again interact. The universe will approach thermodynamic equilibrium, a quiet, featureless state sometimes called heat death. Yet even in this distant scenario, something profound endures. The expansion of space, the fading of light, and the quiet dissolution of matter all follow from the same geometry that shaped the birth of the cosmos. The laws of physics that govern the end are the same laws that governed the beginning. In that sense, the universe carries within it an unbroken continuity, a harmony between creation and decline. But before that distant future arrives, there remains a question of the present. If dark energy defines the large-scale expansion of space, then where exactly does that expansion occur? Does it have a limit? Is there a boundary beyond which nothing exists? To answer that, we must examine the universe as we can see it, the observable sphere of light surrounding us. What lies within it defines what we can know. What lies beyond it defines what we cannot. The next step is to trace the shape of this horizon, the visible boundary of our universe, and to understand how light, time, and geometry weave together to form the edge of observation itself. Every night, when we look into the dark between stars, we are also looking into time. The light that reaches our eyes has been traveling across expanding space for billions of years. The farther we look, the older the light becomes. Some of the faint smudges captured by telescopes today began their journey when the first galaxies were forming, only a few 100 million years after the Big Bang. In each photon, there is a record of distance, expansion, and the slow evolution of the universe itself. This idea that space and time are inseparable defines what astronomers call the observable universe. It is not a boundary of matter or a shell enclosing everything that exists. It is simply the limit of what we can see, determined by the finite speed of light and the age of the cosmos. Beyond this limit, the universe almost certainly continues, perhaps infinitely, but its light has not yet had time to reach us. From our vantage point on Earth, the observable universe forms a sphere around us, centered wherever we stand. Every observer, anywhere in the cosmos, would see a similar sphere centered on themselves. This is not an illusion, but a consequence of how light and expansion work together. The light that defines the edge of our observable universe began its journey nearly 14 billion years ago. But because space has expanded during that time, the current distance to that light is far greater, about 46 billion light-years in every direction. This means that the diameter of the observable universe is roughly 92 billion light-years, an immense sphere containing hundreds of billions of galaxies. And yet, this sphere is not an edge of reality. It is an edge of knowledge, expanding with every passing moment as more light from the distant cosmos reaches us. But even as new light arrives, other regions of space slip beyond visibility, their light forever unable to catch up with the accelerating expansion. The cosmic horizon grows and recedes at once, balancing the reach of light against the growth of space. What lies beyond this horizon remains unknowable in practice, though not necessarily in theory. The equations of cosmology allow us to infer that the same physical laws govern those unseen regions. Inflation suggests that the universe is either infinite or so vast that our observable portion is but a tiny fraction of the whole. Each point in space, no matter how far apart, participates in the same expansion, carried along by the growth of space-time itself. There is no center to this expansion and no outer boundary where it ends. The concept of an observable universe can be difficult to reconcile with our ordinary experience. In daily life, a horizon is something physical, the line where the sea meets the sky, or the edge of a mountain seen from afar. But the cosmic horizon is different. It is defined by time, not by distance alone. It marks the limit of what light has had time to cross since the beginning of cosmic expansion. It is a temporal edge, not a spatial one. If the universe were to last forever, the horizon would shift, revealing new regions while others vanish beyond reach. Within the observable universe, the pattern of galaxies forms a three-dimensional tapestry, a record of how matter has clustered and evolved. Each galaxy is a snapshot of the universe at a different age, seen as it was when its light began its journey. When astronomers look at distant galaxies, they are looking backward in time, seeing cosmic history stretched along the line of sight. The nearest galaxies show the universe as it is now. The farthest show it as it once was, a young cosmos still taking shape. This layering of time and space reveals a profound truth. Observation is never static. The universe we see is not a single moment frozen in time, but a cross-section of its entire history. The deeper we look, the earlier we see. Our telescopes are not just instruments of sight. They are time machines, revealing how the cosmos evolved from near uniformity to complexity. In this sense, the observable universe is not just a limit of perception, it is a map of becoming. Every photon carries a piece of the story, from the cosmic microwave background, the afterglow of the moment when light first escaped matter, to the faintest galaxies at the edge of detection. The deeper we peer, the more clearly we see the universe not as a place, but as a process, an ongoing expansion of space, time, and possibility. Beyond our horizon, the universe continues to expand, carrying regions away from us faster than light can ever bridge. This does not violate relativity, because nothing moves through space faster than light. It is the metric of space itself that stretches. These distant regions will forever remain beyond observation, disconnected not by walls, but by time. Their reality is certain, yet they are unreachable, like pages in a book written beyond the end we can read. The existence of this cosmic boundary changes how we think about our place in the universe. It reminds us that we do not see reality as it is, but as it was, a mosaic of ancient light shaped by expansion. We are surrounded not by emptiness, but by memory, by the lingering glow of events that happened long before Earth or even the Milky Way existed. The night sky is a fossil record, every photon an artifact of the universe's unfolding story. And still, the question remains, if the universe has no center, no edge, and no outside, what does it mean to say it expands? Into what does it grow? To answer that, we must turn from what can be seen to what can be understood, the nature of space itself, and how it can expand without stretching into anything beyond it. When we gaze into the vastness of the night sky, we see more than distance. We see the deep layering of time itself. Every pinpoint of starlight, every faint galaxy carries information from a different era in the universe's past. The farther the light has traveled, the older it is, and the more it tells us about how the cosmos has changed. The universe is not static, and what we observe is not a snapshot, but a story. One written in light stretched thin by billions of years of expansion. From Earth, the observable universe forms a perfect sphere centered upon the observer. This symmetry is not unique to us. It is true for every being, anywhere in the cosmos. Each observer, whether on a planet orbiting a distant star or within a far-off galaxy, looks out upon their own observable sphere, defined by the time light has had to travel since the beginning. This is one of the quiet wonders of relativity. There is no absolute center to the universe, no privileged vantage point. Every location is as central as every other because space expands uniformly everywhere. The limit of our view, the farthest light we can detect, comes from the cosmic microwave background. This ancient radiation, released when the universe was about 380,000 years old, marks the moment when the cosmos became transparent. Before that time, light could not travel freely. It scattered constantly among charged particles in the hot plasma of the early universe. When the temperature dropped enough for atoms to form, light broke free and began its long journey across space. That journey continues still, reaching us today as a faint, uniform glow. The cosmic microwave background is, in a sense, the oldest photograph of the universe. It shows us the cosmos not as a collection of galaxies, but as a nearly featureless expanse of faint radiation. The echo of the Big Bang's heat, cooled and stretched by billions of years of expansion. Small temperature variations in that glow, mere differences of a few millionths of a degree, reveal the seeds of structure, the places where gravity would later gather matter to form galaxies and clusters. Beyond this visible horizon, space certainly continues, but its light will never reach us. Expansion ensures that some regions recede faster than light, not through motion but through the stretching of space-time itself. These regions are not elsewhere in a larger container. They are part of the same universe, simply beyond the reach of communication. The cosmic horizon is a limit of connection, not of existence. To picture this, imagine standing on a shoreline at night, watching waves fade into the darkness. The sea does not end where you stop seeing it. Light and distance merely hide what lies beyond. The same is true of the universe. Our instruments can extend the horizon, but they cannot erase it. Even the most powerful telescope cannot outrun time itself. The diameter of the observable universe is about 92 billion light-years. This number seems paradoxical, since the universe is only about 14 billion years old, but it makes sense once we remember that space has expanded during that time. Light that left a distant galaxy when the universe was young has been traveling through an ever-growing cosmos. By the time it reaches us, the galaxy that emitted it is now far farther away than it was when that light began its journey. Within this observable sphere are perhaps 2 trillion galaxies, each containing hundreds of billions of stars. Yet this immensity is only a fraction of the whole. The total universe may be infinite, or it may curve back upon itself on scales beyond our ability to see. Inflation, the rapid expansion that occurred in the first instant of time, implies that the universe is vastly larger than what can ever be observed. We see only one small patch of a much greater whole. The observable universe, then, is not a physical boundary, but a horizon of knowledge. It expands as time passes, allowing new light to reach us, even as distant regions slip away beyond detection. Every moment, the sphere of what we can see changes, growing slightly larger while carrying within it the entire history of cosmic evolution. We live within a bubble of visibility, bounded not by walls, but by time. Understanding this horizon reshapes our sense of place. We are not observers peering outward from the center of creation. We are participants in an evolving geometry, living within a finite window of perception that moves forward with the flow of time. Everything we know, every atom, every beam of light, exists within this moving boundary. It is not just a limit of sight, but a measure of the universe's age. As we reach for light from the farthest galaxies, we are also reaching for the earliest moments of existence. When the James Webb Space Telescope peers into the infrared, it is looking back more than 13 billion years to a time when the first stars were igniting. Those faint red smudges are not just distant objects, they are living fossils, their light stretched by expansion into the long wavelengths that now reach us. Through them, we watch the universe build itself, one photon, one moment at a time. Every measurement, every image, and every calculation confirms a single truth. The expansion of the universe is not something happening far away. It is happening everywhere, including here, including now. Space itself is growing, carrying galaxies apart, stretching light, and defining the limits of what can be seen. Beyond the edge of sight, that expansion continues, indifferent to our awareness, endless in its reach. And yet, this horizon, though it defines what we cannot see, also hints at something more profound, that the universe may not need an outside to grow. The expansion happens not into something, but within itself. To understand this idea completely, we must look beyond the limits of perception to the nature of space itself, and to the subtle question that has lingered since the beginning. If the universe expands, what is it expanding into? For centuries, human imagination pictured the universe as a kind of stage, a vast container in which stars and galaxies moved like actors beneath a cosmic dome. Even after the discovery of expansion, that image endured. When we hear that the universe is growing, we instinctively picture it ballooning outward into some surrounding emptiness, as if space were a bubble floating in a greater void. But the truth is far stranger and far more profound. The universe does not expand into anything, it expands as itself. This distinction is subtle yet essential. To say that the universe expands into something implies that space exists within a larger environment, like air inside a room or water inside a bowl. But space is not a substance that occupies a container. It is the container itself. It is not made of something that spreads through an external void. Instead, it is the very framework of reality, the geometric fabric that defines distance, direction, and time. When this framework changes, expansion occurs, not outwardly, but internally. A familiar analogy helps, though even it cannot capture the full truth. Imagine a balloon with tiny dots drawn on its surface. As the balloon inflates, each dot moves away from every other, yet none of them travel across the surface. The surface itself stretches, and distances increase. For a two-dimensional being living on that surface, there would be no awareness of the third dimension into which the balloon expands. From their perspective, the universe simply grows. Our universe behaves in a similar way, except in 3 spatial dimensions rather than 2, and with no higher dimensional space outside it. In this sense, the phrase expanding into nothing is misleading. There is no outside to expand into. The concept of nothing beyond the universe has no physical meaning because space and time themselves define existence. Asking what lies outside the universe is like asking what lies north of the North Pole. The question presupposes a direction that does not exist. Einstein's general relativity explains this with elegant precision. Space is not a fixed arena in which events unfold. It is a dynamic structure, shaped and reshaped by the matter and energy it contains. When cosmologists describe the universe as expanding, they mean that the metric that measures distance between points in space is changing with time. Galaxies remain largely in place relative to the expanding fabric. It is the scale of the fabric itself that grows. The distances between clusters increase, not because galaxies fly apart through emptiness, but because the yardstick used to measure them stretches. This understanding dissolves the idea of an external void. The universe is all there is, not because nothing lies beyond, but because beyond is a meaningless word in this context. Space has no edge where it ends, and no surrounding medium where it sits. It is self-contained, governed by the geometry of its own curvature. Whether it is infinite or wraps back upon itself in a finite but unbounded form, there is no boundary to cross, no emptiness waiting beyond. When we look at distant galaxies, we see them receding, their light redshifted by the stretching of space. But there is no central explosion sending them outward. Every observer, everywhere in the universe, sees the same pattern, galaxies moving away in all directions. This uniformity is the signature of an expansion that happens everywhere at once. The universe grows, not from a point, but from itself. The idea that there is no outside challenges our most basic intuitions. We are beings who live in bounded spaces, who measure, build, and inhabit containers. Our language is shaped by these experiences, but the universe defies such simplicity. It is not a thing within another thing. It is the totality of what can exist. Its expansion is not a journey outward, but a transformation of the very fabric of being. In modern cosmology, this expansion is described by the scale factor in the Friedmann-Lemaitre-Robertson-Walker metric. The equations show that space can stretch indefinitely while remaining unbounded. This is why distant galaxies can appear to move away from us faster than light without violating relativity. It is not the galaxies themselves moving faster, but the intervening space expanding. Light traveling across that space is carried with the flow, its wavelength stretched along the way. Even the concept of nothing gains a new meaning in this context. What we might call empty space is not truly empty. It is filled with quantum fields, fluctuating energy, and the potential to shape the geometry of space-time. The vacuum itself has structure. It can expand, it can carry energy, and it can influence the fate of the universe. The nothing into which we imagine the cosmos expanding does not exist, because emptiness, too, is part of the universe's fabric. In the far reaches of the cosmos, expansion continues uniformly. Every region of space expands at the same rate relative to its local conditions. There is no outer edge racing ahead, no bubble boundary advancing into darkness. The expansion is intrinsic, woven into the behavior of the universe itself. Whether infinite or finite, it is complete unto itself. To visualize this, imagine not the balloon, but the fabric of space-time as a flowing river. Galaxies are like boats carried by the current. They are not propelling themselves through water. The river itself moves, carrying them apart. The expansion of space is the movement of the river, not the motion of the boats. There is no need for an external ocean for the river to flow into. Its existence is its own reality. And so the question expanding into what begins to dissolve. It is not a flaw in our understanding, but a limit of our imagination, bound as it is to experiences of inside and outside, motion and containment. The universe transcends those categories. Its growth is self-referential, an unfolding of its own geometry. Beyond what we can observe, this expansion continues without interruption. Whether it extends infinitely or loops back upon itself remains uncertain. But what we do know is that the universe's expansion is not the spreading of matter through pre-existing emptiness. It is the deepening of existence itself. Space does not fill a void. It creates the void as it grows. And as expansion carries distant galaxies beyond our horizon, another question emerges, one that reaches even further. If the universe has no outside, what lies beyond the limits of what we can ever see? What happens in the regions forever, beyond our cosmic horizon, where even light can no longer connect us? To explore that, we must turn our attention beyond the limits of observation, to the frontier between what physics can describe and what it can only infer. If the universe does not expand into an outside, then what lies beyond the part we can observe? This question takes us from the edge of visibility to the edge of comprehension itself. We know that the universe is larger than the portion our telescopes can reveal, but how far it extends and what happens beyond our cosmic horizon remains unknown. To explore this boundary is to step into a space where physics meets philosophy, where the known dissolves into the possible. The observable universe, the sphere of everything from which light has reached us, is bounded by time, not by walls. The light from galaxies farther than about 46 billion light-years away will never reach us because space expands faster than light can cross it. Those galaxies still exist, but they are forever disconnected from us. The boundary between what we can see and what we can never see is called the cosmic event horizon. It marks the outermost limit of communication. Even if we could live forever, light from beyond that horizon would never arrive. But what happens beyond that invisible divide? General relativity tells us that space-time continues smoothly. There is no break, no wall, no physical boundary where the universe ends. The laws of physics that hold within our observable region likely hold beyond it as well. The same geometry, the same matter, the same expansion, continuing indefinitely. Inflation theory suggests that the universe is vastly larger than what we can see, perhaps infinitely large. If inflation lasted even slightly longer in some regions, they would have expanded far beyond our horizon, unreachable in both space and time. This idea leads naturally to the concept of the multiverse. If inflation occurred not just once, but as a continuing process, it could create countless regions, each one a separate bubble universe, expanding within its own portion of space-time. These regions would be causally disconnected, each with possibly different physical constants or laws. Our observable universe would then be one such bubble among many, isolated forever from the others by the unending growth of the inflationary field. It is an idea both fascinating and speculative, still far beyond observational proof. Even without invoking other universes, the regions beyond our cosmic horizon remain part of the same space-time continuum. They are simply too distant for information to travel between them and us. In a sense, they are part of the universe's future, places whose light has not yet and may never reach us. We can infer their existence through mathematics and cosmological principles, but we cannot see them, measure them, or ever interact with them. They belong to a realm of perpetual silence. Somewhere in those unreachable depths, stars are being born, galaxies are colliding, and civilizations may rise and vanish without ever knowing of ours, all beyond the veil of observability. Their sky would look much like ours, filled with light from their own horizon, their own cosmic history. Every point in the universe carries its own observable bubble, each unique yet governed by the same physical laws. This symmetry is one of the most remarkable features of reality. No place is special, and every observer sees the same unfolding pattern from their own perspective. The boundary between what we can see and what we cannot is not static. It changes with time. As expansion accelerates, more regions of the universe cross beyond the cosmic horizon. Light emitted today from very distant galaxies may never reach us in the future, even though it is on its way now. The horizon is both an edge and a moving frontier, retreating faster than any spacecraft, faster than light itself. The universe's expansion carries away the possibility of future connection, slowly isolating our cosmic neighborhood from the rest of reality. This fate, though isolating, is not tragic. It is the natural consequence of geometry and time. The universe is not a place of boundaries, but of evolving relationships between energy, space, and light. To live within it is to inhabit a dynamic reality, one that continuously transforms. We are witnesses to a specific epoch, a moment when expansion is measurable, galaxies are visible, and the afterglow of the Big Bang still fills the sky. The universe will not always be so open to our gaze. To imagine what lies beyond our horizon, we can think of space-time as a vast, unending ocean. We drift upon it, surrounded by waves of light that have managed to reach us. Beyond the edge, the ocean continues, but its waves are forever out of sync with ours. The horizon is not the end of the sea. It is simply the limit of the waves that can reach this shore. When we ask what the universe expands into, we are really asking where the horizon of existence lies, whether there is a larger framework, a greater reality beyond space-time. But as far as science can tell, there is no beyond. The universe is self-contained, complete within its own dimensions. The expansion does not require an external void. It is the change of its own geometry. The question, into what, becomes unnecessary. Space does not need an outside to grow. Growth is its nature. Yet, even in this self-contained reality, mystery remains. The accelerating expansion ensures that most of the universe will remain forever hidden. Its regions beyond the horizon will never send their light to us, and their stories will remain untold. The observable universe is not all that exists. It is merely the portion that light and time allow us to know. As we stand beneath the stars, surrounded by ancient light, we find ourselves in a fragile window of cosmic visibility. We are small, but our awareness spans billions of years and light years. We see not the whole, but enough to understand its nature. The universe expands not outward, but inwardly, deepening its own structure. What lies beyond sight is not an outside realm, but the continuation of the same cosmic fabric, infinite, unbounded, and endlessly evolving. To grasp this truth is to let go of the image of a universe pushing through emptiness. There is no emptiness beyond it. The universe is the emptiness, and that emptiness is alive with energy, geometry, and time. Space does not grow into nothing. Nothing itself grows into space. And so, the question changes once again. It is no longer into what the universe expands, but how space itself continues to evolve. The answer to that question leads us beyond the horizon, into the domain where time, geometry, and existence blur together, and where the story of the universe becomes the story of space-time itself. To stand beneath the night sky is to look across a boundary that is both infinite and intimate. Every star, every faint shimmer of light from distant galaxies, represents a fragment of the cosmos that lies within our reach, within the domain where light and time have conspired to make seeing possible. But there is more beyond what any eye or telescope can perceive. The universe extends far past the limits of observation, into regions where light will never arrive, and where time itself bends away from what we can know. To understand the true nature of expansion, we must explore that unreachable frontier, the horizon that divides the visible from the forever unseen. The cosmic horizon is not a physical barrier. It is not a wall at the edge of space or a curtain concealing another realm. It is simply the line drawn by light's finite speed and the unceasing growth of space. Because the universe expands, distant regions recede from us faster than light can bridge the gap. They do not move through space faster than light. Rather, space itself stretches so rapidly that even light emitted in our direction can never arrive. These regions are beyond our event horizon, beyond the possibility of causal connection. This means that most of the universe, perhaps the vast majority, will forever remain hidden. We can calculate its existence, infer its geometry, and predict its evolution, but we can never touch it, never receive its light, never send a message that reaches it. Those regions exist within the same cosmic fabric, but on a page of space-time, we can never read. From their perspective, we are the ones lost beyond the horizon. Each region of the universe carries its own bubble of visibility, its own observable cosmos bounded by the reach of its own light. This limitation is not a flaw in physics, but an essential feature of relativity. The speed of light, constant and unyielding, defines the maximum rate at which information can travel. As space expands, the distance light must cover grows faster than light itself can move through it. The result is a horizon not of material edges, but of temporal boundaries, a frontier in time. Every second, the universe writes new regions out of our possible future, carrying them beyond the range of interaction. In the observable universe, we still see echoes of the time when everything was closer. Distant galaxies appear as they were billions of years ago, because their light has taken that long to reach us. We are surrounded not by the present universe, but by its past, a cosmic fossil record made of light. The galaxies we see at the farthest distances are no longer where they appear to be. The expansion of space has carried them away, stretching the light they emitted long ago. In many cases, the galaxies whose ancient light we now detect no longer exist in the form we see them. We are observing ghosts of the past, luminous memories drifting through time. What, then, exists beyond that? Inflation theory suggests that our observable universe is only one small region in a vastly larger whole. If inflation continued beyond our local domain, it would have stretched other regions far beyond our sight. Each of these could be as large and complex as our own observable cosmos. Some versions of inflation even predict an eternal process, a bubbling multiverse in which countless universes expand, collide, or remain forever separate. Each would have its own physics, its own geometry, its own history. Though we may never confirm such realms directly, the mathematics of inflation makes them plausible. But even within a single connected universe, the concept of beyond the horizon carries deep meaning. It tells us that the universe we inhabit is finite in what can be known, but not necessarily finite in what exists. Beyond every horizon, new horizons unfold. The structure of space-time itself ensures that no observer can see all of reality. Each point of view is unique, bounded by time and distance, yet embedded in the same infinite continuum. This realization transforms our understanding of cosmic expansion. The universe does not expand into an external space, nor does it expand from a single point. It expands within itself, carrying all points apart as time moves forward. The regions beyond our horizon are not out there in a larger void. They are simply beyond what our light can reach. If we could somehow travel faster than light, the horizon would shift, revealing new regions. But no matter how far we went, there would always be another horizon beyond. The boundary of knowledge moves with us. In this sense, the horizon is not a limit of the universe, but a mirror of our own finitude. It reminds us that observation is bound by time, and time itself is woven into the structure of space. We are not standing outside the universe looking in. We are inside it, moving with it, expanding as it expands, seeing only what the geometry of space-time allows us to see. The cosmos is vast beyond comprehension, yet every observer, everywhere, experiences the same confinement within their own sphere of light. What lies beyond our horizon may never be known, but its influence is not absent. The uniformity of the cosmic microwave background, the nearly identical temperature in all directions, suggests that the regions now beyond reach were once close enough to interact. Inflation stretched them apart faster than light could travel, freezing that uniformity into the structure of the cosmos. The universe we can see carries within it the imprint of the universe we cannot. There is an elegance in this limitation. It gives the universe depth, not just in space, but in meaning. The horizon defines not an end, but a perspective. It is the edge of the knowable, the meeting place between what is measurable and what is imagined. Beyond it lies the unobservable continuation of the same laws, the same fabric, extending without end. To look beyond the horizon, then, is not to search for another world, but to recognize the boundaries of our own. The cosmos we see is enough to reveal its nature, even if not its totality. We know that expansion continues, that the universe grows not outward, but through time itself, and that beyond our horizon, this process unfolds endlessly. If there is mystery beyond the horizon, it is the same mystery that surrounds us here, the mystery of existence, of geometry, of the laws that make being possible. The universe does not hide its secrets in distance. It expresses them everywhere, in every particle, every photon, every curve of space. The unseen beyond is not separate from the seen. It is the same fabric, stretch beyond our capacity to perceive. And so, the question changes once again. The universe is not expanding into anything, nor bounded by what we can see. It expands as a consequence of its own nature. The next question becomes not what lies beyond, but what it means for the universe to expand within itself. The answer to that takes us to the final reflection, where science meets philosophy, and where the story of expansion becomes the story of existence itself. The universe does not expand into something. It expands as something. That something is the fabric of reality, space-time itself. Every galaxy, every atom, every pulse of light exists not within a static background, but within a geometry that evolves. Expansion is not motion through emptiness. It is the growth of the very stage upon which existence unfolds. When we look at distant galaxies, we are witnessing the evolution of that geometry over time. The expansion we see today is the continuation of a process that began more than 13 billion years ago. A process not of explosion, but of unfolding. Each moment in cosmic history adds a new chapter to the story of space-time's transformation. In that sense, the universe does not expand outward. It expands forward into its own future. This idea reshapes what we mean by existence. The universe does not sit within a larger space waiting to be filled. It is the space, and that space is dynamic. The growth of the cosmos is the evolution of its metric, the mathematical rule that defines distance and time. To say that the universe expands within itself is to say that reality changes scale while remaining whole. Every region of space participates equally in this growth. No edge advances, no boundary recedes. The expansion is everywhere and nowhere all at once. Even now, as galaxies drift farther apart, they do not move through the cosmos like ships crossing an ocean. The ocean itself swells, carrying them gently apart. Within galaxies, gravity remains strong enough to resist this stretching. Stars stay bound together, planets remain in orbit. But across the vast intergalactic voids, expansion reigns unopposed. It acts not as a force pulling things outward, but as the steady deepening of spacetime's own fabric. The future written by this geometry is vast and quiet. As dark energy continues to dominate, the rate of expansion will increase. Distant galaxies will fade from view, their light stretched until it can no longer reach us. Over trillions of years, only the closest galaxies, bound by gravity, will remain visible, eventually merging into a single island of stars adrift in endless night. The cosmic microwave background will fade into undetectable wavelengths, and the sky will grow dark. Stars will exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even those remnants will decay. Black holes will evaporate through the faint glow of Hawking radiation, releasing their last energy into an ever-cooling universe. In the farthest future, only a thin mist of particles and radiation will remain, the faint whisper of existence stretching toward infinity. This final stage, sometimes called the heat death, is not an ending in fire but in silence, a universe that continues to expand, its energy spread too thin to form structure or sustain change. And yet, even in this distant vision, expansion continues. Space will still grow, time will still flow. The universe will not collapse or stop. It will simply become more diffuse, more subtle, more ghost-like. The same laws that governed its birth will guide its quiet eternity. The expansion of space-time, the very act of reality growing within itself, is the thread that connects its beginning, middle, and end. This continuity carries a profound meaning. The universe's expansion is not a story of escape, but of transformation. From a dense, hot origin to a vast, cold expanse, the cosmos evolves without ever leaving itself. It is a single, self-contained system that changes form but not essence. Every atom, every beam of light, every moment of consciousness participates in that evolution. We are part of the expansion, made of the same fabric that stretches, the same geometry that curves, the same energy that fuels its growth. When we ask what the universe expands into, we are really asking where we ourselves are within that expansion. The answer is both simple and profound. We are within it, inseparable from it. We are not observers outside the cosmos looking in. We are expressions of its unfolding geometry, as much a part of its expansion as the galaxies or the light that connects them. To exist is to expand with the universe. The idea that the universe expands within itself invites a new perspective on what nothing means. True nothingness, a state without space, time, or law, cannot exist within the framework of physics. Even the vacuum of space hums with quantum energy, with fluctuations that shape space-time and give rise to particles. Emptiness is never truly empty. It is a field of potential, a quiet sea from which the visible universe emerges. In this sense, the expansion of space is not the invasion of nothingness, but the flowering of possibility. From that perspective, every second of existence is an act of creation. Space grows, time flows, and the cosmos becomes larger not because it is moving outward, but because it is becoming more itself. The distance between galaxies increases, but so does the depth of reality, the unfolding of time. The universe does not expand into emptiness, it expands into being. When the first humans looked into the night sky, they saw mystery. Today, with all the knowledge of cosmology, the mystery remains, but it has deepened. We now understand that the universe is not a fixed arena, but an evolving entity. Its expansion is the motion of reality itself, the rhythm of existence written in geometry. What began as a singular moment of birth has become an ongoing transformation, carrying everything forward in the silent expansion of space-time. If there is beauty in the cosmos, it lies in this, that from the smallest quantum fluctuation to the largest galactic cluster, everything participates in one grand motion, the universe growing within itself. There is no outside, no boundary, no destination, only the eternal unfolding of space and time, carrying with it every star, every planet, and every thought that wonders at its meaning. The universe is not stretching into emptiness. Emptiness itself stretches, carrying with it every atom, every spark of light, every moment of being. What expands is not matter through void, but existence through time, a cosmos that grows not beyond itself, but as itself. And so, the great question that began this journey, what is the universe expanding into, finds its quiet answer. It expands into nothing because there is no outside for it to fill. It expands within itself because expansion is its nature. It expands because to exist is to evolve. The universe does not stretch into emptiness. Emptiness itself stretches, carrying with it every star, every galaxy, every moment of existence. What expands is reality itself. And yet, as the universe continues its silent expansion, a final question lingers, one that no equation can quite dissolve. If space and time themselves are growing, what then gives birth to their growth? Does the fabric of reality unfold from some deeper layer of existence, hidden beneath the reach of physics? Or is expansion the shadow of something even greater, a pulse of creation that never truly stopped? Perhaps beyond the limits of time, beyond the horizon where light itself surrenders, there lies a truth not about distance, but about meaning, a mystery that no telescope will ever see, yet one that every atom quietly remembers. For all we know, the universe may not be expanding outward at all, but inward, into the depths of its own infinite self.